I'm Riza Batista-Navarro. I don't really use the Theresa, but it's okay. So today I have the pleasure of talking to you about how we've used natural language processing, or NLP, in the context of trying to estimate the carbon footprint of food. So hopefully this is something very relatable to many of us, because well, everybody eats, and maybe many of us are into cooking or preparing food at home specifically. So the inspiration of this project basically started during the COVID pandemic. So we applied for funding, which was in the context of how do we build back from COVID. So we were thinking, hang on, one of the things that came up as part of or as a result of the pandemic or the lockdown specifically, is that a lot of people have rediscovered the joys of cooking at home. So I'm not going to go into a lot of detail in the interest of time, but basically this shows that 40% of people, when they were answering a survey or responding to a survey, said that they will be cooking more at home, and then many of them said that even after the pandemic, they intend to continue this kind of practice. So then we thought that this is a nice opportunity. While in terms of nutrition of food, there are some tools available to a lot of people. For example, when we go to supermarkets, we look at products that we buy, the food that we buy. There's like a traffic light system telling us if this is, high in sugar, high in salt, and so on. But there's not much yet in the way of telling us how much carbon footprint this food is basically, or the environmental impact of this food. So we wanted, or the overarching aim of this research project that we embarked on is essentially to encourage people, or to raise the awareness of people about the carbon footprint of food, so that we can help them to reduce the carbon footprint. And essentially, like I said, we want to make this information more accessible to people. So in this project, we have kind of two basic assumptions. As I said earlier, we're only working within the limitation of one type of food environment, which is eating and cooking at home. So we're not addressing the environment of eating out, for example, or getting a takeaway, and so on. So we obviously did a quick test of our assumption, which is that people actually cook more at home, and also that people actually use online recipes. Because when I talk about natural language processing, you can probably predict that I'm gonna be using recipes or web-based recipes to do that sort of analysis. And indeed, we saw a trend, which is that during those 2 or 3 lockdowns we had during the pandemic, there's a spike in terms of number of people accessing. Well, here we use a generic website, All Recipes, but we use the UK kind of a subset of it, not the US one. Right, yeah. Now, you might be wondering, well, surely somebody has tried to address this problem. Partially, yeah. So what's out there currently are what I refer to as online calculators. So if you go to these 2 websites I provided, so the one called Plate Up for the Planet is a carbon food calculator. So essentially, you input every single ingredient, the amount of that ingredient, and so on, and then it will estimate for you the carbon footprint. And then the other one here, you input the details of your cooking devices. So for example, if you're using the oven, how long you're using the oven for, and so on. Then again, it will calculate the carbon footprint. The question though is, who has the time to do all this inputting, right? So if you're going to cook, right, you're starving or whatever, the last thing you're probably going to think of is, oh yeah, let me go online and let me put in each one of these ingredients. So you see what I mean? So there are tools out there. The question is, who has the time to engage with those tools if you have to go into detail? So before I get into what we actually did, to try to fully automate that process using natural language processing, let's just have a quick overview of what's actually in the cooking recipe. So you're all familiar, but just to highlight, obviously we have a list of ingredients. For each ingredient, we probably have some amounts, right? And the units of measurement used there. Sometimes the ingredients are given in a vague way. So it says 2 large onions. What do you mean by large? Yeah. And we also have a list of instructions, or the methods that one has to use. So for example, you have to preheat the oven, you have to use a certain temperature for how long, or you have to bake something again for how long. And sometimes, again, it's ambiguous. In this example, it says for 30 minutes, but you can also have a recipe which says bake until brown. how long is that exactly, right? So it's a bit tricky. So clearly, I guess I should give the disclaimer now that this is not going to be a perfect solution, right? So we're going to make some assumptions. But yeah, so this is just like an overarching, an overall diagram of our approach using natural language processing. So if you look at the box which says NLP, so essentially we have developed techniques for tasks called name entity recognition and entity linking, and I'll go into detail in those two in a bit. Those are able to parse the ingredients and to basically understand the amounts, the means of measurement, what food exactly is being used. However, what's still ongoing work for us is understanding the cooking actions. So if you're going to bake using an oven, or you're going to fry, and so on. So we haven't dealt with that yet. So what we have, though, to empower our NLP is a knowledge base, and this knowledge base, as you might predict, contains the information about the actual carbon emissions. So for example, a slab of meat, from a database, we probably have information as to how much carbon footprint that slab of meat has. This project, as you can see here, is a collaboration with an SME called Emission. So the life cycle analysis was done by them. It's their expertise, and my expertise is on the NLP and data science side of things. So at the end of the day, what we really want to obtain here are some calculations, right? So yeah, saying that for this recipe, this has much carbon footprint, and for each serving of that recipe, this is it has that much carbon footprint. So I'm going to go into detail into those two NLP tasks that I described. So name entity recognition. So I have this here, a simple example. So this is I should say maybe simple task of picking up names from text, right? So here I have a generic example, which is, it's like a news article where I have highlighted names of organizations, people, and places. So similarly, we can do something similar for food, right? So we need to identify the amounts, the units of measurement, and the actual name of the food. And here, it's a nice intro from the previous talk, which mentioned in their last slide, transformers. We made use of an approach that builds upon transformer models. So transformer models are the same models underpinning what we now know as ChatGPT and GPT, right? Okay, so this is a language model that knows a lot or has learned a lot about the English language. But on its own, it cannot do name entity recognition. So what we did is, on top of that, we added a layer that is capable of predicting whether each token belongs to a certain type of name. So for example, in this case, this token, Janet, is the beginning of the name of a person. Yeah. So we took this approach and we applied this to the food domain. So that process is called fine-tuning. Yeah. And for those who are familiar with the BERT model, so BERT is one of the most popular transformer-based models. So we took BERT, we fine-tuned BERT on gold standard annotations for food. And we got, just to be in the interest of time, we got very good results. So I'm proud to show the actual results of name entity recognition for a particular example recipe. And you can see here that if this is these are the original ingredients, these are automatically extracted amounts and units of measurement, and these are the automatically recognized ingredients. But that's just the first step, because I'm nowhere near kind of getting the actual carbon emissions. So this is where we use entity linking, or we develop approaches for entity linking. This is the task of looking up a certain name in some database or knowledge base. So this is an example where you have the name 49ers, for example. You want to be able to link that to the page for San Francisco 49ers, let's say. So so for those who are wondering, hey, isn't that an easy task? Why don't you just look it up? If you have a name, right, why don't you just look it up in Wikipedia? It's not really that easy, because we're dealing with natural language, so we have ambiguity. So if somebody says pepper is one of my favorites, can be referring to red pepper, black pepper, and so on. But there's also variation. Yeah. So if a recipe says eggplant, right, and the database has aubergine, or maybe vice versa, then you have to be aware of synonyms to be able to pick up both. Same with chips and fries. So we formulated again a machine learning based approach. First, we considered, can we take this as a multi-class classification problem? But that's not feasible, because we're dealing with 600 plus food items in our database, so that means 600 classes, so that's not feasible. So instead, we consider it as a binary classification problem, where we say, given a name from a recipe and a name from a database, figure out whether they are similar to each other or if they are the same as each other. So we consider it as a semantic similarity approach. So for that, we've had to develop our own knowledge base, essentially a very UK-specific one, which contains more than 600 food ingredients used in the UK. And then we run a survey amongst users to collect recipes. We didn't want to assume that a lot of people use BBC Food or whatever. So we wanted to run a survey and say, okay, give us a list of recipes that you often make use of. And then based on those URLs, we got the actual recipes, and from that we created our own data set or our own corpus. Now, this is where machine learning kind of, a lot of machine learning tasks has a lot of challenges. We need labeled data, okay, as with many tasks, as with every time we create our own new data sets, and we have to engage with experts to actually label the data so that we can teach a machine. So that happened. We engaged with people to manually label some data, and then we trained a model for that semantic similarity problem by generating these types of examples, where we say positive examples, let's say eggplants and eggplant, eggplants and aubergine, but negative examples for eggplants and egg, and eggplants and egg noodles. We trained the model, but here we didn't want to rely only on deep learning-based approaches, so we wanted to take advantage of the strengths of unsupervised approaches, where we simply measure similarity between two strings. And based on the result of that, if the similarity is high enough, then we take that as the final output. Otherwise, it goes through a deep learning approach, which uses another type of transformers called sentence transformers to filter out those pairs. And finally, using those filtered pairs, we put them into a support vector machines model, which is, for those who are familiar, one of the more traditional machine learning-based models. Anyway, putting all this together, we have a web browser plugin, a Chrome extension, which basically shows for any recipe you navigate to the carbon footprint in a traffic light system. And just to summarize, this is a user-based evaluation showing that when people saw that information, they basically reduced the amount of carbon based on the recipes that they are intending to cook. And finally, to wrap up, we are currently developing a mobile app version of the plugin. And next steps would be to come up with a way to suggest substitution. So I guess that's the one that I'm really interested in pursuing, which is, if you have a high carbon ingredient, what could be a substitute? Because it is becoming a very difficult task, especially, let's say, if you have egg, because egg can be used in different contexts. So with that, I'd like to end, and if anyone is interested, please feel free to get in touch with me if you want to give a try the mobile application especially.
Thank you. We have time for one quick question, if anyone has one. Yeah, at the front.
Yeah.
Thank you very much for the presentation. I just wanted to know if this model can be used to calculate carbon footprints in food wastage.
In food?
Food wastage.
Food wastage, yeah, okay, yeah.
And just secondly, can this model be used in another industry as well?
In another industry, another sector.
Yes. Sir.
Yeah, I guess because it's highly reliant on NLP, so it depends on the availability of textual data. Yeah, so if you have kind of a lot of information kind of buried within textual data, then I guess yes. But also, if there is a database, like what I said, we have to develop our own database or knowledge base of food. So these techniques will work well in that context. So it depends on the problem, really. But in principle, yeah, as long as you have those resources, you have a knowledge base, you have some information in text, then you can use these techniques to do that. But of course, like I said earlier, if you're using machine learning-based models, then there's a lot of work that goes into coming up with labeled data, for example. So it's not just a matter of kind of taking a model and then applying it. You have to train it, or in this case, you have to fine-tune it. Yeah.
Thank you very much.
Yeah.
Lovely.
Okay.